Yes, welcome students to the next recorded session on the lab program number 9, which is uh, writing an embedded C program to display the hello world message using LPC2148 internal UART. This is the ninth lab program, the program to display the hello world message or any message which you like to display using the internal UART of LPC2148. Now in the previous lecture video, that is recorded lecture video 12, now I have explained you the communication interfaces. So the two communication interfaces. One is onboard communication interface and another one is the external communication interface or product level communication interface. Now UART is one onboard communication interface, meaning universal asynchronous receiver and transmitter. So this is onboard communication interface or on-chip communication interface, which will allow the components within the embedded system to communicate. So again, this universal asynchronous receiver and transmitter is an asynchronous serial communication interface. Now why we say asynchronous? Because to synchronize the sender and the receiver, so there is no clock cycles that are being used here. So the sender and the receiver, they are synchronized by a predefined agreement. That is what happens in a synchronous communication interface. Since UART is an asynchronous communication interface, there is no clock cycles used for synchronizing the actions between the sender and the receiver, or synchronizing in the sense if the sender is too fast than compared to the receiver, limiting the sender, and if the receiver is too fast in receiving the data than compared to the sender, limiting the receiver. That is what is basically the synchronization. And here the synchronization is not done by using the clock cycles, but the synchronization is done by using a predefined agreement or a predefined contract, and by adding some additional bits. So this is what in the previous class I've explained more on the UART, universal asynchronous receiver and transmitter. So now we'll try to understand how to display the hello world message or any message which you decide to display using internal UART of LPC2148. Now, as already mentioned, UART stands for Universal Asynchronous Receiver or Transmitter, because this can receive the data also, at the same time it can also transmit the data. Is a serial communication protocol. Why it a serial communication protocol? Because it transmits the data serially bit by bit. So it cannot transmit the data at a time. What it does, it transmits the data serially bit by bit, one bit at a time. So asynchronous serial communication is widely used for byte oriented transmission, and in asynchronous, that means you're sending it bit by bit. So but generally used for transmitting the byte oriented transmission. In asynchronous serial communication, a byte of data is transferred at a time. So and again, this is how it looks. So it is serially bit by bit, but so you send 8 bits at it, one after the other, so a byte get transferred to the other device. That is what is a byte of data transmitted at a time. So you don't have all the 8 bits going simultaneously to the other receiver. It is one by one. So a bit will follow another bit. Like this, 8 bits you can send. After this byte is received, then you can initiate transferring the next byte. Now this is the simple diagram. I have this is one peripheral device UART here, and this is another device which is also as UART, and again this has transmitter and receiver, this has transmitter and receiver. So the receiver of this is connected to the transmitter of this, and the transmitter of this is connected to the receiver, and they can communicate asynchronously by serially sending the data bit by bit. Now UART frame structure, because the frame structure is very important here, because UART is not using the clock cycles for synchronizing the sender and the receiver. Now we'll see what kind of frame structure the UART uses. So since it is a serial communication protocol, uses a frame structure for its data type. The frame structure in asynchronous communication consists of all these things. Now before we go here, just have a look here. This is the basic frame structure. I have a byte here. This is my actual data byte which I want to transfer from one device to the another device. Now this is a byte. You can see how many bits are there. 8 bits. 1 2 3 4 5 6 7 8. This is the byte which is my actual data that needs to be transferred from one UART device to the another UART device. And so this is not the only thing which I'm sending. Now I have the start bit here and the stop bit also, just to indicate, just to tell the receiver, this is where the byte starts and this is where the byte ends. You got to add additional start and stop bits. So this is a start bit. Remember, the start bit in UART is always low and the stop bit in UART is always high. Now the start bit is there just to say that indicate that the serial communication has started, and it is always low. And between the start bit and the stop bit, you have the actual data bits which are in here. I've shown 8 data bits, but UART also allows you to send the data packet of size 5 bit to 9 bit. You can send 5 bits data, you can send 6 bits data, you can send 7 bit data, you can send 8 bit data, you can send 9 bit data also. But what I've written in this frame structure is now 8 bit. Normally we send 8 bit data packet. Now stop bit is to indicate that this is the end of the first byte, and I'm using the stop bit, and the stop bit is always high. So this is what the frame structure we follow, and this is what the common agreement, that pre-agreement which I mentioned. So this is what this also comes under that pre-agreement. Both sender and receiver, they'll agree on this common agreement. Next, LPC 2148 UART. Now if we speak UART with respect to LPC 2148 microcontroller, now this LPC 214 itself has 2 inbuilt UARTs available, and they are called as UART 0 and UART 1. There are 2 inbuilt UARTs available within the LPC 2148. And now the question also says, now you got to display a hello world message using internal UART, that is the built-in UART of LPC 2148, and you should know how many UARTs are available in LPC 2148. LPC 2148 has got 2 UARTs, UART 0 and UART 1. So we can connect 2 UARTs enabled devices at a time to LPC 2148. In case I want to connect the UART enabled devices to the LPC 2148, now how many such devices I can connect to LPC 2148? I can connect 2 such UART enabled devices to LPC 2148 at a time, because it has got 2 built-in UARTs available. Now UART 0 and UART 1, now they are identical to one another, so they're the same. Now except the fact that UART 1 also has a modem interface included, but you don't find modem interfaces included in UART 0. Okay, we have 2 built-in UARTs available, LPC 2148 and in LPC 2148, that is UART 0 and UART 1, and they are identical. And one additional thing that you find in UART 1 is it has an interface for the modem. That means you can also connect the modem to this. But which UART we are going to use in our program? Are we going to use UART 0 or UART 1? Now we are going to use UART 0. In our program we are using the UART 0. Now UART pins, it has 2 pins. Obviously it should have 2 pins. One is the output pin, another one is the input pin. Now output pin is the transmit data pin, or the serial transmit data pin, because it sends the data bit by bit to the other device. And RxDO is again serial receive data pin, so which receives the data serially bit by bit from the other device. So these are the 2 pins of UART 0, and we don't discuss the pins of UART 1 because we are not using UART 1 here. Now what we are using is UART 0. We'll focus on this. Now you understood there are LPC 2148 got 2 UARTs, UART 0, UART 1, and they are identical, and only additional feature that is found in UART 1 is modem interface is also included. But what we are using is UART 0, and it has 1 transmission pin and 1 receive pin. Now it's time to understand the UART 0 registers. Now UART has got many registers, but in our program we use few of them. Now it is necessary to have the knowledge of those registers which are used in our program, which displays the hello world message on displays the hello world message using the internal UART. Now there are many registers, but what we are doing here is we are going to discuss only those registers which are really necessary for us to write our program. Now without understanding these registers, it is not possible to understand the program. So just try to understand the registers first. Now we have a register called as this U0 LCR. Now U0 stands for, this is the register which corresponds to UART 0. And similarly for UART 1, if I say UART 1 also, you'll find the register LCR, and there it is called as U1 LCR. Now since now we are using UART 0, now the register is U0 LCR. What is this LCR? It is called as line controlled register. Now how many bit register it is? It is an 8-bit register, 8-bit read write register. That means this register can be read and you can also write to the register. So it is an 8-bit read write register. Now what it determines? It determines the format of data character that needs to be transmitted or received. Now I got to define in what format the data must be transferred or received. Now that format I can define by using ULCR. I was telling the pre-agreement or the pre-contract, so that this register U0 LCR plays a major role in that agreement. Now it determines the format of the data character that needs to be transmitted or received. Now it's an 8-bit read write register which can be read also, which can be written also. So this is how it looks. Now we have 0 to 7, 8 bits, and the first 2 bits are reserved for specifying the word length. Now when sender is sending to the other receiver, the sender and the receiver, they must agree on the word length. Now how many bits make the word length? So that is specified using these 2 bits, 0 to 1. And the next one is the number of stop bits required, and the start bit is always low, it is reserved. So and there is no bit reserved for the start bit is always low. And how many stop bits are required? Whether I need 1 stop bit or whether I need 2 stop bits, whether I need 3 stop bits, that you can specify by using this particular bit. And then 3 is enable parity. Now when data is being sent from the source to the destination, after the destination receives the data, is there a scope for that to test the data, check the data, parity. In the previous class when I was explaining the communication interfaces, I told ART parity and even parity. Now when the sender is sending, if there are in the data that the sender is sending to the receiver, if there are odd number of ones, it will add 1 to that in order to make it as even parity, and the receiver there again counts the number of ones and verify that number of ones with the parity bit that is added. So if you require that also, for that this is reserved. And even parity select, there is one more, stick parity, set break, and we don't use all these things. What we use is this. We will focus on these 2 bits, we'll focus on this, and we'll focus on DLAB, that is divisor latch enable bit. So divisor latch access bit. Okay, these are the things. Now I have the explanation here. Bit 1 and 0. So 0 and 1. So they are reserved for word length select. Now if I want to make 5-bit characters as 1 word length, then I have to give these 2 as 0 0. Now if I want to use 6-bit, so I have to give 0 1. If I want to make 7-bit as 1 word byte, then I have to make it as 1 0. Now what I'm made in red color because this is what we use. Now I make 8 bits as 1 word, 1 byte. So I'll be giving these to 0th bit and first bit of line control register as 1 1. Next, now bit 2. So this is the bit 2, the number of stop bits. Now here the number of stop bits. Now if you give 0, if bit 2, if you're making it as 0, so there is only one stop bit. If you make it as 1, you can add 2 stop bits. Now we are restricting it to only 1 stop bit, and we are not using any parity enable and parity select and break control we are not using. And bit 7 again we are using, and the bit 7 will be made as 1, enable access to divisor latches. Now this why I'll tell you, because there are 2 clocks One is the CPU clock and other one is the peripheral clock. CPU clock will be always higher than the peripheral clock. Now if I take LPC214 itself, its clock frequency is 12 megahertz, but the peripherals which are found inside that LPC2148 will operate at lower clock frequencies. And just to make the baud rate adjustment with respect to that, we are using this enable access to device latches. I'll explain in my next slides with the formula. So but now this is required because there are two clocks. One is the CPU clock, another one is the peripheral clock. The peripheral clock is always lesser than the processor clock. And just to enable that, we got to make the 7th bit as 1. So this is made as 1 right now. So we are not interested in these things. We are interested in this, we are interested in this, and we are interested in this. This I got to make 1 in order to enable the divisor latch accessible bit, and this is 0 because only one stop bit is sufficient for me, and I'm making 8 bit as 1 byte. So I have to make these two as 1 1. Now when I do that, this is what the data I get. Now U0 LCR is equal to this 7th bit is 1, the rest all is 0, and the last two, and this is 0 because only one stop bit is required, and the 0th bit and the first bit is made as 1 1. So and what is the data? It is 83. This is 8 and this is 3, 83 in hexadecimal, 0x83. So this is what the data which is required in order to agree on the common format. Okay, next. Now apart from that line control register, this is the line control register. So we also have something called as U0 DLL. So that is divisor latch lower and divisor latch most significant bit, divisor latch least and divisor latch most. These are the two registers available here. Is the divisor latch LSB, as I already told, divisor latch MSB, and again these are 8-bit read write registers. Now to access these two bit registers U0 DLL and U0 DLM, so DLAB must be made as 1. That is what I showed you in the previous slide. So DLAB is made as 1. If you're not making this DLAB as 1, so then these two registers you cannot access. Now we require these two registers. Why we require these two registers, I'll tell you. Now we got to find actually the content, what should be the value assigned to these two registers. Now UART divisor latch least, UART divisor latch most. Now this is an 8-bit register, this is an 8-bit read write register. Now if I combine them together, they will become a 16-bit register. So that is the reason this is LSB and this is MSB. And now if I want to write them in order, first I'll be writing U0 DLM and next I'll be writing U0 DLL because that is the least and this is the most. Next. Now how to find this U0 DLL and U0 DLM of UART 0. So this is the formula used. Now U0 DLM, this is the most significant byte and this is the least significant byte, is equal to PCLK divided by desired baud rate into 16. Baud rate also I told in the previous class. So it is the number of bits transmitted per second. Number of bits, and again both the communicating parties should also agree on this baud rate. Now desired baud rate into 16. This is the formula. Now I told there are two clock frequencies. One is CCLK, so that is CPU clock frequency. For LPC21748 it is 12 megahertz. And there is one more called, this is PCLK, whatever written, it is peripheral clock frequency, and the peripheral clock frequency is less than the CPU clock frequency. Now how to find this peripheral clock frequency? You have to divide if for LPC2148 you got to divide the CPU clock frequency by 4. Now that is CCLK by 4. CCLK is 12 megahertz. 12 megahertz by 4, that is 3 megahertz. So 3 megahertz is the peripheral clock frequency. Now the desired baud rate required for communicating between the sender and the receiver is 9600 bits per second, and this is the standard baud rate. Now how do I find? Now let me apply this in this formula. Now I have found the peripheral clock as 3 megahertz. Now U0 DLM plus U0 DLL is equal to this. So 3 megahertz, 3 followed 3 megahertz. So 3 followed by 6 zeros divided by 9600. Desired baud rate is 9600 into 16. I got it as 19.5. Now we cannot use the fraction here because you cannot write fractions to what the registers. That is why I am taking it as 19. 19 is taken. And if it is 19.6, then I would have taken it as 20. Now since it is 19.5, I have taken it as 19, and 19 in hexadecimal is 0x13. Now when I write this 0x13, now and together these two register is 16. This is 8-bit register which acts as MSB, and this is the 8-bit register which acts as LSB. Now what goes to this? Now this is my data. I got 13. Now this UDLM is 00 and UDLL is 13. Now when I combine them together, so it is a 16-bit data, 0x0013. So this 0 is this 0 and 13 is this. This is what I got. Now using this formula and with the desired baud rate of 9600 with the CPU clock frequency of 12 megahertz, I found that the peripheral clock frequency must be 3 megahertz, and for this 3 megahertz clock frequency, what should be the U0DLM and U0DLL? So U0DLM is 00 and U0DLL is 13. This is what I have found. So this you have to find, this you have to calculate like this. Now if you take some other microcontroller, and if its CPU clock frequency is say 15 megahertz, then again this will vary. Okay, I hope you understood how to find U0DLL and U0DLM. Now to find these two and to assign, if you're not making this DLAB1, so it's not possible for you to access this U0DLL and U0DLM. Now if it's not possible for you to access this two, then the clock frequency that is supplied even for the peripheral will also be 12 megahertz, and the peripherals will not operate with 12 megahertz clock frequency. That is the reason you got to find out U0DLM and U0DLL. So 3 megahertz clock frequency. Now setting U0DLM and U0DLL to 13, so this 13 value will reduce the clock frequency of PCLK, peripheral clock frequency, to 3 megahertz. Now that was the two registers which you understood, U0DLL and U0DLM. Next, there is one more important register, U0THR, that is transmit holding register. So the data which you want to transmit, or the byte which you want to transmit from to the one to the other, should be assigned to this register. The moment you assign it to U0THR, UART 0 transmit holding register, so the data will be sent to the other device. And it's again 8-bit write only register. U0THR cannot be read, it is write only register, whereas this register, these two are read write registers, and LCR, line control register, is also a read write register. But U0THR is only write only register. That means you can only write to this register, but you cannot read from this. Now the data to be transmitted is returned to this register. The moment you write it, it goes to the other device, intended receiver. Now the divisor latch bit in this line control register that we understood, the 7th bit, it should be made as 0 before writing to U0THR. That means yeah. Now here I defined it as, here I defined it as 1. Now I define it as 1 and I perform this computation. I compute the value that should be assigned to U0DLL and U0DLM. After computing this, and before writing the data to U0THR, DLAB should be made to 0. That means when you are writing the data to U0THR, you cannot have DLAB enabled. So you are enabling DLAB only to find U0DLL and U0DLM. The moment you find it, so again you reset back. Now after resetting back, so this is 0 now, 0. So this is the value 0, 3. 0, 3. U0 LCR is assigned. It's an 8-bit register. One second. It's an 8-bit register. So many zeros are not required. It is an 8-bit register. So this is 4 bits and this is 4. 4 plus 4, 8-bit. 8-bit register. Now this 0 corresponds to this. These 4 zeros corresponds to this 0, and this 0 0 1 1 corresponds to this 3. Now we have only so this 0 is saying there is one stop bit is used, and this 1 1 is saying so 8 bit sequence of 8 bits is forming a byte. Next, and there is one more register, U0 LSR, line status register. Again it is a write bit read only register. Now why we are using this line status register? Line status register is used to check whether the data transfer is done or not. The moment you write the 8-bit data to this, I said the data will go to the other device. Now how do I know the data has gone to the other device, whether the data transfer is complete? In order to check that, I'll be using the line status register. It is an 8-bit read-only register. Again, in this line status register, I don't require all the 8 bits. In order to check whether the data transfer is done, we should focus only on the 5th bit. You can see here, so many 8 bits are there, and even I'm not going to explain all these bits. All these things are not required. We'll focus only on the 5th bit, THRE. So this one. 5th bit. Now transmitter, so THRE is this, transmitter holding register empty. Now if this, the 5th bit is 0, if this particular bit is 0, it means that the U0 THR, the previous register which I told you in the previous slide, U0 transmit holding register as valid data. That means it has not yet transmitted. Now if this particular bit is 1, now U0 THR is empty. That means it has already transmitted the content to the other device. Now by examining this 5th bit of line status register, you can tell whether the data transfer is complete or not. Now if this particular bit is 1, it indicates the data transfer is already complete. If this particular bit is 0, the data transfer is not yet complete. Now with this understanding, now how many registers you understood? So all these registers are very